So CFA and HIDA, I think, are both very interdisciplinary, right? So, and we are really embracing this. So I've worked a lot with numerical models, so classic air pollution forecasting models, weather forecasting models, and climate projection models. And then on the other side, we have a lot of experts of KRT for Earth observations, big measurement campaigns, and so on. So quite unique data that we can build on top of sort of the typical widely available data for ERA5 and so on that you've seen in the previous talk. And I really see machine learning as the bridge here that allows you to, on the one side, of course, develop methods. So for example, causality. Is Peter Bauer still here? Not sure. He will talk about this on Thursday, I guess, in more detail. So to try to think about how can sort of new methods, either for the geoscience or more generally, help us to advance machine learning, to get autoregressive rollouts, stable over long time scales for weather forecasting, for climate change projections, but then also the central science challenges. So I think Maximilian also touched on this a bit, but my key focus may be uncertainty in climate change projections, and I will illustrate this a bit more later on. So how can we reduce uncertainties in a projection where we don't have observations for yet, right? So again, we have seen maybe 30, 40 years of satellite data, high quality satellite data, but we want to project hundreds of years into the future under different scenarios. And this, you will see, brings intrinsic uncertainties. And then the other thing is, of course, building better numerical models in the first place. The numerical models being those Earth system models with the equations that Maximilian printed out quite literally, right, that we have to solve numerically because there is no analytical solution. So we have to solve them numerically. That's expensive. So machine learning can speed those models up or potentially improve them, for example, through hybrid models or machine learning parameterizations for processes we can't resolve. So at KRT, I give a lecture about machine learning for climate and environmental science. So I just took the topic of the Lehrstuhl, of the chair, and put it into a master's Vorlesung, so a lecture, and exercises where we do a lot of hands-on work as well. But most of my students, there are some physicists, some meteorologists, but most of my students are computer scientists. And then usually I give a brief introduction to climate science in a nutshell, which usually is also much longer than just 10 minutes or so, but Maximilian has covered most of this. So I will just skip through this very, very quickly. So clearly, I think we can all agree on global warming is happening, right? And this has a global signal, right? So if you just look at the global warming integrated record of these anomalies, plotted as a surface map, and Maximilian already talked about, this probably being, at the beginning you could have seen that Antarctica is completely missing because we didn't have observations. But as you look at anomalies relative to 1950 to 1980, how this map just turns more and more yellow and more reddish. So global warming is happening, and this is happening at a very fast rate, especially over the last few decades, as you can see on the right side. And you can also see that, especially, maybe given that the pointer is working so badly, we'll just do this here. The last few years were particularly warm, and 2023 was sort of record-breaking. So if you look at the entire monthly temperatures from 1850 in dark blue to, because it's getting warmer, right, to 2022 and then 2023, and you look from January to December, you can see that there's sort of a big gap in the seasonal cycle, so later on during the year in terms of the temperature anomalies later during the year. And 2024 was quite similar. So this is one of the questions we are trying to answer, right? Can we use machine learning tools to detect and attribute, for example, what of this gap that we see here is already climate feedback, so climate change signal emerging, or is it just unusual internal variability and so on? And maybe later on I will come back to this. So clouds, for example, could play a role. But also clearly ENSO and so on, Niño variability that Maximilian mentioned. So Maximilian showed the equations and said they were not particularly pretty to look at, right, the dynamical equations. But if we think about the Earth system, it's actually partly a thermodynamic, but also importantly a dynamical system, right? So if you look at just, so this is actual reproduction of weather systems for the year 2024. And you can see that there are little named storms running through here, or bigger storms, right, around the tropics. Then you can see that there's different types of oscillations and fluctuations in terms of weather variability going on in the tropics compared to the mid-latitudes, for example. and you can see that it's a very dynamical system, right? So that's the one part that we want to model, the fluid dynamical equations that Maximilian wrote down and that we wrote down and we have to model forward. And basically what you see in terms of dynamics here is cloud systems moving, right? Because everything else is clear sky. So clouds, you can already see, cover a large part of the world and play a very important part in Earth's energy budget as well. That brings me directly to the next point. So this, now we are in June 2024. So this is what happened. We have to model this. I have to leave this somehow. This way. But as you already could see in the clouds, we don't just have to model a fluid dynamical system, but we have to model also a thermodynamic system, so an energy balance. And under climate change, we are particularly interested in the energy balance. And there's, of course, a lot of energy exchange happening just naturally. So we have sunlight coming in, shown in yellow here, right? And a part of this is absorbed in the atmosphere through water vapor, CO2, ozone, and so on, oxygen. A part arrives at the surface, right? A part of this is directly reflected back to space. Others are absorbed at the surface. Different types of surfaces have different reflectivity. So this is why ice albedo, for example, is a big factor. And then on the right side in orange here, we have the greenhouse effect. So the long wave radiation, because we are on a basically hot body, right? That also emits radiation back to space, that longer radiation than what is coming in from the sun, because the sun is much hotter. And part of these thermal emissions from Earth are basically absorbed within the atmosphere, right, and scattered back and so on. And this is the greenhouse effect, keeping our system in a, for us, good state in the first place due to the natural greenhouse effect. But of course, as we emit more greenhouse gases into the atmosphere, like CO2, or due to CO2, the atmosphere heats up, can hold more water vapor. We get basically an anthropogenic greenhouse effect that can bring us, as we see nowadays, you saw it in the first slides, out of the balance that we are accustomed to as human species recently. And then also the water cycle clearly plays a big role in terms of evaporation from the surface and then also condensation again higher up in the atmosphere. An important sort of central point here in this entire figure is that clouds play a big role as well, because a lot of the sunlight is reflected by clouds, but clouds can also act like greenhouse gases, so absorb thermal long wave radiation. So depending on how, so historically speaking, clouds are cooling climate, right? So they're mostly reflective. But there are also clouds, especially higher up in the troposphere, which actually have mostly a greenhouse effect. And depending on how clouds change under climate change, because you change atmospheric humidity, you change temperature profiles, you change the circulation as part of which clouds form, you could potentially have an amplifying or dampening effect on global warming. And that's a big research question, large part of the uncertainties looking forward, because we cannot resolve those clouds, as Maximilian said. So we are not able to resolve individual clouds globally under many different climate change scenarios nowadays. And again, this is where machine learning can come into play. So this is exactly, I think Maximilian had it on the right side, I've got it on the left side. He got a plot from the MPI, I've got it from the IPCC. So I guess the IPCC rules over the MPI, so my plot is better. But otherwise, it's the same. So clearly, when we want to model climate, we have to not just represent clouds, right? But we have to model all sorts of different processes. I just heard in the break about new processes in the ocean that we'll hear about, and that might not be represented so well yet as a carbon feedback, because part of it is also we emit CO2 into the atmosphere, right? And how much of the CO2 goes into the ocean is absorbed in the ocean by biogenic processes or on the land by vegetation and so on. And clearly, because this is very complex and requires a lot of equations, we already needed computer models to do this since the Nobel Prize winning work, right, from the early general circulation models in physics recently. So this is, computational work for a very long time, but computationally heavy work, right? And working with very complex equations, partly, or unknown equations in many cases, which opens the door for machine learning. And also we have to do this not just because we don't know what the humans will do in the future. We can't just do this for one single scenario. This is what we are going to do, right, over the next 100 years, but we have to run this under different scenarios of human development, how many CO2, methane, aerosols, and other forcing agents, as we call it, we emit to the atmosphere and therefore change the system. So this is not working when I have the pointer. So we have clearly more So numerical models, again, we cannot solve many of these equations analytically, especially the fluid dynamical equations, so we have to discretize them on numerical grids, both in the horizontal and in the vertical. Some of the models go up into at least parts of the ionosphere, right? But and clearly you have the same problem going down into the deep ocean, right? So if you want to model heat transport, changes in atmospheric oceanic circulation, like the thermal Halian circulation, so AMOC, Atlantic Meridional Overturning Circulation, tipping points of the climate system, you have to model this as well. And very often we use much more complex numerical grids than this nowadays, but this is just for illustration purposes. So again, this is expensive. So in Karlsruhe we have nicely a National High Performance Computing Center, or in German it's NHR, called HORICA that we use, but there are many other places like this in Germany. Okay, so what I would like to highlight today in terms of processes compared to Maximilian is maybe a bit more applied and a bit more coming from the climate science perspective of what are long-standing problems that we have to solve and how can machine learning help us here. And one aspect that we might go into first is also an idea of hybrid modeling, but where you still have most of the Earth system model that you had originally, but you just replace one component, like in this case atmospheric chemistry, by a machine learning model, because atmospheric chemistry you can actually resolve on these grid scales nowadays fairly well, at least, but it's very computationally expensive. I'll come back to this later on. And this is where machine learning can obviously help, because the alternative is that, well, the process is ignored. So in many climate change simulations, you would just not represent the process, right? And that's also maybe not such a great idea. And then there are the sub-grid scale processes that we simply cannot resolve on such a grid-by-grid point basis, especially for global models and for not just sort of local high-resolution models or so. And this would be clouds. I will talk about this, but also, for example, aerosol microphysics and so on. And there are basically two strategies. One popular one is, again, parameterizations, learning better parameterizations to implement into Earth system models in the first place. Maybe a slightly different strategy I talk about today is to look at sort of an ensemble, a bunch of models that has already been run for the IPCC. Okay, and then afterwards look at the observational evidence, which of these models might be closer to it, and then say, okay, which of these models are more realistic. And here I see just one of the many routes how machine learning can really change the field, and has already changed it, in my opinion. So now I think Maximilian was very considerate, because he must have read my abstract. He talked in his abstract about uncertainties, but you hardly showed them, right? So thank you. So I will briefly just show you what I mean by tackling uncertainties in climate change projections by looking at a coarsened surface temperature projection, so just surface air temperature, what we feel today basically in Berlin for a 5 times 5 degree grid location in Central Europe. This is actually not a square, but more of a, because we're on a regular grid, yeah, it's not really square, but just for dramatic purposes, it's overemphasized here. And this includes, for example, Karlsruhe and KIT. I think it's just next to Berlin, but I think it broadly applies to Berlin as well. And what we look at is basically climate model simulations for this grid location in Central Europe. First of all, historically, and compare this to observations, and then also later on for future scenarios. And what is basically shown here is, in black, an observational data set, okay, following this line here. So this is what actually happened. And you can see that broadly relative to, I think this is the 1900 to 1930 mean here, okay, that it has already warmed significantly. Maybe we're now at maybe around 2 degrees warming in the latest years in this grid location. And then in gray, you see basically realizations from 34 climate models relative to the self-consistent baseline, or pre-industrial baseline. 34 different climate model projections. So this would be climate models produced in Canada, in the US, in Germany, in Japan, in Russia, in Australia, you name it. All different realizations. And what you can see is that sort of the gray lines here have their own wiggles, their own internal variability, because it's not a weather forecast. We cannot forecast weather more than a few weeks in advance. So they have their own realizations of internal variability, but that broadly speaking, so the envelope of these historical, so climate model simulations forced with historical assumptions about CO2 emissions, aerosol emissions, methane emissions, and so on, that they broadly follow this trajectory up to, I think this is 2014 or so, when the models were stopped for historical simulations. And then what you cannot do for observations, clearly, but you can do for climate models is to say, okay, what happens if we assume now a business as usual scenario, so the entire world does a fossil fuel-driven industrialization, right? So we just keep going with very high CO2 emissions. And under these assumptions of high CO2 emissions for the future, map this out up to the year 2100 or so, okay? So these are the same 34 climate models. What you can see is that all models agree that warming is continuing to happen, right? So there's agreement that global warming and also as a result regional warming will not stop, but there's a large variability or uncertainty in this. And similarly, you could ask yourself, okay, alternative scenario, we try to keep below 2 degrees global warming, for example, which still translates into higher regional warming over the land surface. And this would be a strong mitigation scenario, for example, where all 34 models sort of level off and then maybe show a slight decline even in temperatures towards the end of the century, but still show significant warming based relative to pre-industrial levels. And now, from a climate risk point of view, you might be interested then, okay, what is this temperature going to be? This is annual mean. You could also look at extreme temperature shifts as a result of it. What is going to be the local warming by 2050? And that would be, of course, a bit of a noisy answer, right? So what is the warming in 2050? And clearly one issue is that every year in any model can be particularly warm or particularly cold, right? So there is internal variability that for any given year can give you a hot or cold year still even in a much warmer climate. So from a climate statistics point of view, you could say, okay, if I applied a smoothing algorithm to take out most of this internal variability and just plot the average change or the median change and maybe then 95th to 5th percentile of the change of the distribution, it would look something like this. And then you could say, okay, by 2050 or by 2100, I have a given scenario uncertainty in the mean, for example. So the average projection under 2100, under this high emission scenario, would be around 6 degrees warming. And for the strong mitigation scenario, would probably level off again towards 2 degrees warming or so for the average of 34 models. And this is what we would refer to as scenario uncertainty. But then the big elephant in the room, clearly, and this is what we are focusing on partly in my group, is the large model uncertainty or structural uncertainty that if you would just take the raw archive of CEMA projections, so the Coupled Model Intercomparison Project that I referred to here, then for this central European grid location, you would have a warming somewhere between 3 and 10 degrees of warming, and this is not very helpful, let's say it this way, right? So often when I show this plot to just general scientists, let's say it this way, they say, well, do climate scientists then not know what is going on, right? Basically, okay, it's warming, but not much more you can really tell me, right? And that's of course not true. We know that not all models are created equally. Not all of these models are equally good. And around 2010 or so already, people really started sort of to revolt against just taking the ensemble as the information, but to say, okay, which of the models are actually better? Can we weight those projections? Can we start ruling out some of these projections to get a tighter grip on these uncertainties? And I would argue, and maybe this is quite intuitive, that based on the historical record that we have already seen, for example, from internal variability relationships that we have seen for clouds, for example, we might be able in a high-dimensional space to use machine learning to get a tighter grip on this. Because just historical warming, for example, here, you saw that most models followed sort of the envelope of historical warming. This doesn't seem to be a good metric, right? Because, well, maybe they got the right answer for the wrong reasons. They had aerosols are historically cooling, CO2 is historically warming, maybe they were offsetting biases and so on, right? So you cannot just rely on very simple metrics, but maybe in a high-dimensional space you can evaluate these models much more sensibly. And Maximilian already touched on this in a few different ways, and there are clearly many different perspectives on this and many different options. But time allowing, I will briefly touch on 3 large ideas that we are sort of pursuing to basically use AI or machine learning to advance climate modeling in this regard. And again, I think Maximilian said they can be faster or more accurate, right? I just put it as better, which is even harder to quantify, I guess, whatever that means. So the first idea is parameterizations, which could potentially make these models faster, but also potentially better if it allows you to represent processes maybe more closer to observations or represent processes in the first place, that otherwise would be too computationally expensive. Then there's emulation later on, which is mostly after going faster at the moment, but potentially you could also make projections better. And the third idea is then later on combining satellite data observations and model projections to reduce uncertainties. So to motivate the first point on parameterizations, because when you talk about hybrid models, you saw neural GCM, which is basically, okay, I still take the dynamical core, right? But all the other processes, clouds, probably even aerosols are somehow nudged into this, but they didn't really explicitly represent those. Everything else is a parameterization, right? Everything else is machine learning. I just model the fluid dynamics. And this is, of course, sort of going back to the very rudimentaries of climate modeling, which is we start off with fluid dynamical equations, actually not even radiative transfer anymore then, but anyway, very simple systems just represent the core fluid dynamical equations maybe as a dynamical model, whereas then Earth system modeling really over the decades has built up much more to represent higher parts of the atmosphere, we touched on this today, or carbon cycle components, or aerosol components, and so on, cryosphere components. So they became increasingly complex. And I sort of come back from this side of the spectrum and say, okay, if I look at some of these components here, where could machine learning actually help to make models more computationally efficient and potentially also better by allowing, for example, more models to include atmospheric chemistry? Because atmospheric chemistry shapes the composition of the atmosphere. It's important for a variety of greenhouse gases that lead to global warming, for example, ozone, methane, and so on. But it's still not represented in many climate change projections. So here it's shown for the 2010s onwards, but if you looked, for example, at the CMIP projections I showed earlier on, then around 60–70% of those models would not include interactive atmospheric chemistry. And the reason for this is, even though it's very important, so this is maybe first a motivation slide, so why should we include it? Because, as I said, there are species like ozone, methane, different types of aerosols that are being formed, particulate matter, that are shaped by atmospheric chemistry. And that is, for example, important for modeling the future of the stratospheric ozone layer, which is not just important in terms of ozone hole, but also more generally globally. And also because it's an air pollutant in the troposphere and so on, but also a greenhouse gas. So we want to model these species. But the reason why we don't include atmospheric chemistry is that it's very expensive. So climate models, state-of-the-art climate models, if you want to run them on a supercomputer, a typical simulation maybe takes a month or two, right, if you run it at fairly high resolution. And that's significant on a PhD timescale as well. At least European PhD timescale. Yeah, atmospheric chemistry, and I've done this myself, can easily slow down these simulations by a factor 2 or 3. It really depends on the complexity of the scheme, but a typical complexity you would run in a global climate model slows down a model like this by a factor 2 or 3. So instead of 2 months, you have to run for 6 months, potentially. So that's really critical, right? And this is why many PhD supervisors then say, atmospheric chemistry, maybe let's keep it out of the model, right? We make this assumption, let's keep it out of there. And the reason is, well, if you want to model atmospheric chemistry, you have a lot of chemical species like ozone, for example, that are long-lived enough to actually be part of transport. So you don't have to just model the transport of the entire atmosphere with just fluid parcels, right? But you have to model the transport of individual chemical species. So instead of having one tracer in there, suddenly you, or maybe 2 or 3 for water vapor or so, you suddenly have 50, 30, 40 different tracers to transport around. And on top of this, you have some chemical species that are involved in multiple chemical reactions. So ozone, for example, you can see here. And if you have 150 or 200 of these chemical reactions, then you have basically a coupled system, right? A coupled system of differential equations that you have to solve. Again, numerically, you cannot solve these analytically. So this becomes very expensive very quickly, long story short. And this is also why, so I suffered through that PhD journey to a certain degree because my PhD supervisor was very, very much into atmospheric chemistry. So I decided immediately afterwards, can we do this faster using machine learning, right? And again, long story short, yes. Okay, so this was my own little success story there. So I suggested already sort of 2017, 2018 to basically look into existing simulations that had been run and build a parameterization that you could flexibly build into different climate models that basically does for especially types of simulations where this feedback is often ignored. you could basically use machine learning as a mapping function, right, between the physical state and the chemical state, and do this quite efficiently. So I implemented this first with some colleagues from Cambridge, especially Luke Abraham, in the UK Earth system model. So this already happened years ago. And we are now doing this in the German icon art model. So I've heard some people talking about icon in the break. So icon is the co-developed model by KIT, MPIs, and so on here in Germany for global climate change projections. Also now upcoming CMIP 7, so the next intercomparison project. And yeah, there's currently a PhD candidate, Iling, who is doing really great work and has just written up her first paper for submission, where she basically used this idea but put it into eigenart, showed that it runs really stably, and builds on this for additional scenario projections and so on. So first we, of course, tested this parameterization offline, but then crucially what actually has to happen is, so offline machine learning algorithms can be very patient and well-performing, right? So you can get great offline performance, but once you put it into a climate model and integrate, including this parameterization forward for decades or even hundreds of years, these parameterizations can become potentially unstable. But yeah, in this particular case, that's not true, even though ozone and other chemical species can potentially feed back onto the physical state. Basically, with sort of the ideas we implemented here, we got this working stably pretty much immediately. So we had no simulation. I think we had one simulation for the upper atmosphere. So if you include it for the mesosphere, it can become unstable. But for the troposphere and stratosphere, basically, it runs stably for decades and at a fraction of the computational cost. So basically, it adds no computational overhead. And we've also basically trained it first on UKSM data and transported it into icon. We showed that you can train it on one model and its data and transfer it to another model, and it works equally well. So I think this is one way how you can then say, okay, those 60–70% of the models that don't include chemistry at the moment should maybe do this in the future. And I could now walk you through a detailed statistical evaluation of different scenarios. So we've done this for pre-industrial control scenarios and also extreme 4 times CO2 scenarios and so on. And basically, the parameterization, you can throw a lot at it, and it works. Now, I mentioned that chemistry is also important for forecasting, for air pollution, pardon me. So air pollution is clearly a concern, particulate matters, ozone, probably at days like today as well. So ozone is a respiratory irritant, so it can really be harmful to human health as well, and be one of these factors that on heat wave days lead to increased mortality. And Seb Hickman, a PhD student at the University of Cambridge, whom I co-supervised and who recently graduated, and well, not graduated, passed his PhD viva and works now at ECMWF. So he had this really nice paper a couple of years ago now, where he basically said, okay, this is not so much climate modeling, but could I do something similar to weather forecasting, use a transformer model to do air pollution forecasts? And he learned from a huge number of stations across Europe from historical data, and basically showed, yes, you can do this extremely well using something, the temporal fusion transformer. So compared to numerical models, he showed quite competitive performance. So I think it's not just weather forecasting, it's also other types of forecasting where machine learning can really be a game changer, and just for the forecasting task, not inherit those model biases that many numerical models have. Any questions to this so far? Otherwise, I will just keep going.
I still not quite understand the machinery of those two models that you have presented, but I'll ask you during the lunch break.
Okay, cool. Yeah, I mean, it's devil is in the detail. And also, given that Maximilian talked about this earlier on, so I just said, we learned a machine learning parameterization and plugged it into an Earth system model. Here we go, right? There are details depending on which model you have. You can either hard-code it directly in your Fortran code, right? Or you use something like a plugin like ftorch or so to do this.
Yeah, I'll talk to you in more detail, because there are certain parts that I still have to understand.
Okay, yeah, cool. Yeah.
Yeah, I just was wondering if there's a potential to, in the future, to add radio occultation observations to just solve the mesosphere, or at least up to mesopause region.
You mean to directly learn from observations, some sort of representation?
Yes.
There are two potential issues with that. One is extrapolation. So how do you learn a parameterization that is purely based on observations if you want to implement this in a climate model? But maybe you could build something. The second point is, yeah, I like learning directly from observations. It would be much easier if you would just say, I want to make sort of a forecasting tool immediately learning from observations. If you want to do a climate Earth system modeling tool, going also to different climate states, it could inform, for example, through transfer learning, your pre-trained model or something along those lines. So I think there's potential here. It's just you have to be very careful of how you go about it. So it's probably not just going to be, I'm going to fit on data and it will be a good model. But we can also discuss.
Yeah, sure.
Yeah.
I was wondering, because to my understanding, there is some interconnection between all these different layers. I mean, vertical coupling from above and from below. So it's good to see it as a whole atmosphere model up to the upper parts rather than just a specific.
Yeah, that's a very nice comment to make, actually, because yes, so I guess what you're trying to say is sunlight is coming in, and what arrives in the troposphere or at the surface depends on what you have above, right? Clouds are the basic example.
And
also,
vice versa,
yeah,
also the climate change from
yeah,
below.
yeah. So I'm fully on board with that especially for process understanding and true scientific models, with which you would maybe also run science experiments, you would need mechanisms like this, that if I perturb something high up in the stratosphere or in the mesosphere, I want to see a downwards effect, and vice versa, maybe what happens below should happen above. And I think there's currently maybe a slight disconnect between, let's say, the AI forecasting community and the scientific community on machine learning and Earth system modeling, that a lot of these models that do just forecasting can also maybe by now learn directly from observations. But usually they don't think in these terms, right? So they would just have a tool that works good for forecasting under typical conditions, where, for example, the entire stratosphere is just one level, right? So you wouldn't have this resolution of the vertical process. So I think adding more information from different types of observational sources would be potentially useful. I'm not sure how much for forecasting, because you could say maybe there's an indirect correlation that I would learn anyway from the lower levels that informs me about what might have happened at the upper levels, right? So purely as a forecasting tool, maybe you don't need it, I don't know. The answer is, I think no one has tried yet. But if you would include this process, then you could actually use these AI models also for scientific inquiries at some point, right? Because Earth system models you mostly use not so much to have, I want to have the perfect forecasting model, but I want to be able to study my scientific mechanisms, right? And if you don't resolve the entire atmosphere, then clearly this limits you in terms of the questions you can ask, and also causality, if you hear about this on Thursday. Yeah, if your causality is that you have an indirect link at the surface that reflects what happens higher up in the atmosphere, for example, then you will never be able to run the experiment of what happens if I did something else. Geoengineering, for example, these sorts of ideas in the stratosphere. So you would not be able to run the same type of scientific experiments. So yeah, I like that point, but yeah. Okay, if there's nothing else, I might move on to the second bullet point. And again, I think I can go through this a bit more quickly than I originally planned, which is probably good for timekeeping too. So Maximilian already touched on this in terms of emulation and making things faster, but I just want to highlight this again. So once you start parameterizing individual components like atmospheric chemistry and say, okay, this is very expensive, I replace that. You could also ask yourself, well, but I've got these huge data archives from climate model intercomparison projects that are already out there, publicly available. I don't have to pay for it, right? Why do you not just train a machine learning model on these archives and then be able to run much faster additional climate change projections? And I think the logic behind it is sound, because once you have this data available, there's no additional cost to it. And training a machine learning algorithm admittedly costs you something, but it's far cheaper than running a full Earth system model again. And clearly, if you want to explore more scenarios on typical climate change projections like the ones I showed on my initial slides, you don't just have 2 scenarios, but maybe 4 to 6 different scenarios for the future that are played through under different conditions by most models. But not more, right? 4 or 6 scenarios, maybe multiple ensemble members, 2 or 3 ensemble members. Exceptions, again, run large ensembles, but that's very rare. it's hugely computationally expensive to run any such simulation with any single climate model. And now you have the data from these simulations, so could you not just, at least in interpolation space, take this data and look what would have happened if instead of tackling CO2 emissions most drastically, I immediately target only methane emissions, right? Because methane has a shorter lifetime in the atmosphere of around 10 years, so I could reduce methane in the atmosphere very quickly. So you could run all sorts of different scenarios very quickly. Now, when we tackled this problem at first, we felt that especially compared to weather forecasting, where there were already benchmark platforms like WeatherBench that you showed a screenshot from on the evaluation pipeline, that there were not enough readily curated data sets that would make it easy for machine learning experts to really explore climate model emulation at scale. So I've been involved in a variety of projects here, for example, in Canada with Mila, Quebec, and led by Julia Kaltenborn, a PhD student there, where we created a larger data set for climate model emulation, where the basic idea is, again, what I said before. So you have certain scenarios, which are basically your boundary conditions or input for CO2, methane, different types of aerosols. And your Earth system model is typically the converter to certain outputs, key metrics, impact variables that you care about, like temperature and precipitation. And then again, in the archives, usually it's run for 4 to 6 different scenarios, assuming different extremes of mitigation versus business as usual. And you could basically learn from these existing data sets a machine learning model that does the mapping for you, right? Because you have a lot of different samples for a lot of different climate models and years and scenarios, and you could learn from this. And originally we did this for Climate Bench, for a single climate model with a lot of different scenarios and a lot of different data, and basically the data publication climate set then became a set of climate models. So instead of just for one climate model with a lot of data, doing this for the entire CMIP archive. And as I said, we tried to address this gap that on the shorter time scales, we already had a lot of data sets for, especially WeatherBench, I suppose, for weather forecasting, but that on the climate model emulation side, there was this big gap that we wanted to address for machine learners to take this problem on. And so, yeah, you are invited to use this data set too, if you like. So it's easy Googleable, they have their own websites. And just to iterate again, so the entire CMIP archive for CMIP 6 was around 30 petabyte or so. So it's really about problem formulation. You cannot just download all the data, learn on or train on all the data. You need some sort of problem formulation to begin with. And clearly we have worked on this too. So on climate model emulation, I think this would completely be beyond anything I can talk about today. Otherwise I would not talk about anything else. But this is work by Seb Hickman again, whom you saw earlier on for the air pollution forecasting, and a research assistant, Ilya Trajkovic at KIT, and also Julien Boussard from Mila, Quebec. So we looked at climate model emulation from a causality perspective, and also, so maybe I can run through the basic idea. You start with your dynamical state, for example. You do learn some sort of latent representation, then you try in a causal graph, causal representation learning to update a prediction to the next model state. So causality, why causality? Because we do believe that it can give you a structure of relationships in the data that makes these climate model emulators more robust. So again, going back to the original idea, this is mostly still for dynamics, but if you had, historically speaking, seen in a simulation temperatures increasing, CO2 increasing, aerosols increasing, then for a purely data-driven model, it's not clear if the aerosols drove the global warming or the CO2 drove the global warming, whereas actually the aerosol partly offset part of the global warming. So, you know, there are these relationships that in a purely data-driven way might be harder to learn, and where a causal structure can help you build a more robust model. And also, so if you want to do climate model emulation and you do this autoregressively, so you constantly predict the next step from your previous step, then if you want to do a climate model emulation over 100 years and many different scenarios, stability becomes an issue. So we applied a variety of different tricks here to the loss functions, and especially something called Bayesian filtering, which you may or may not have heard about. So this is on the archive now to make this long-term rollout stable, because otherwise we would run into this issue of the AI weather forecasting models, that the models would just diverge and blow up after a few weeks. Yeah, and this is maybe a nice result from this autoregressive rollout that, for example, ENSO, right, which Maximilian talked about earlier on a timescale of around 3 to 7 years. And this is the power spectrum, power spectral density, and the periodicity. And you see there's sort of a peak at 3 years, but also longer periods where the ENSO spectrum has to be represented. And we try to emulate a single climate model here in ORESM. And you can see that sort of the causal representation learning we developed here outperforms sort of naive machine learning algorithms on these longer timescales. So we are better able to capture the long-term variance of surface temperature variability in this case here than just fitting a transformer, for example. Okay, so now I maybe have 5 or 10 minutes to just touch on this final idea, which I think is also very powerful, but methodologically very much simpler for good reasons, I hope to be able to tell you. And this is how we can bring together, once we have climate model projections and Earth observations, to reduce uncertainties. So this goes back to this figure from the beginning. You can do this for every grid point, right? You can do this globally integrated for global warming. But the basic idea is we have some historical observations, also high dimensional of many different variables. And clearly the models in the past seem to not diverge as much as they do for the future, right? For these different future scenarios. And then the key question is what are the drivers behind this uncertainty? We have run a number of different projects, PhD projects, also one larger project funded by NERC in the UK while I was still there on clouds. Because if you look into the actual Earth system model data, you will find that the key factor for increasing CO2 next to carbon cycle is how clouds change under climate change and how this is represented in models. And we've published a number of different studies on this. But then there are also other uncertainty factors that are probably understudied in comparison, like water vapor changes in the stratosphere, which we looked at. And then you can also apply observational constraint frameworks, not on sort of trying to constrain uncertainties in these individual processes. You could also directly target machine learning-wise uncertainty frameworks for changes in precipitation, so rainfall, or for changes in surface temperature. And again, there were different approaches that we've outlined over the years. And if you want to generally have an idea about what people have been working on trying to constrain these uncertainties in future climate change projections, there's an opinion article by myself and Duncan Watson-Paris from UC San Diego on ACP, so Atmospheric Chemistry and Physics, published this year, where we compare these approaches and highlight some of the challenges that I will probably also touch on briefly here. Okay, so if you talk about climate science and if you talk to a climate scientist, then most of them will be very intrigued by clouds, and this is not an acquired taste, but a necessary taste, I would say, because it's driving a large part of the uncertainty in the future projections. So if you go back to even those regional climate change projections, it's not so much how clouds change locally, right, over your given grid point, but how clouds change in the tropics, change the global energy budget, and then you really have to look at it as a holistic system. Where, for example, here you can see for low clouds, so clouds at low altitudes, that you see these massive cloud decks in the subtropics here west of South America, or here and here, right, and also here. And these are sort of semi-permanent features that just reflect a lot of sunlight coming in. And it's also one of the potential tipping points, right? So if these cloud decks were to disappear, that would be quite dramatic, would have quite dramatic consequences, right? So one of the key questions, how stable are these low cloud decks over the oceans, which are highly reflective over an otherwise very strongly absorbing surface. But then we also have high clouds, so clouds very high in the troposphere, sort of close to the tropopause almost, and they have more of a greenhouse effect, even though they also have a shortwave effect, so reflective. And they are mostly focused here, you can see it over the maritime continent and sort of convective centers in the tropics. The key question is, clearly, overall clouds are cooling, but depending on which type of clouds change, so if, for example, the upper troposphere would be more affected than the low cloud decks, then you could even have, or just low clouds are actually increasing, that would also be a possibility instead of decreasing, right? You could have different sign changes of how clouds amplify or dampen global warming. And this is quite literally, if you look at different climate models nowadays, just raw material, right? I'm not saying that all of these are realistic. Some models say clouds are dampening climate change, others are saying it's strongly amplifying, really strongly amplifying. So where's the true answer, right? And strongly amplifying would, for example, be low cloud decks disappear at a rapid speed, right? And cooling would be, oh, these low cloud decks are actually increasing in scale. Or, for example, optical density. This is also illustrated here, so just to show you that I'm not just telling you some sort of rubbish. This is the IPCC AR5 report. So this is sort of summarizing knowledge of different climate scientists and key mechanisms. And what you can see here is that, for example, these high clouds could be rising in altitude. This would change their greenhouse effect because they change basically where they absorb radiation and re-emit, also in terms of which temperature they are at. And then the typically suggested mechanism is that these low cloud covers, which are strongly reflective, are actually decreasing. But again, some climate models don't show that. And then also you have at high latitudes some mechanisms. One that is actually missing is optical depth, because if you warm up the atmosphere, then at high latitudes you have actually a lot of low clouds that are ice clouds, and they could change to liquid clouds, and that changes the optical density, which is a strongly nonlinear feedback potentially. And again, this is under current discussion. So how do climate models capture this? And what we found in this recent paper by Paolo Ceppi et al., in which I was also involved, is that climate models underestimate low cloud cover in the first place, and as a result also seem to underestimate its decrease. And this has, again, strong implications. So you saw earlier on one of my earlier slides that recently we had very warm years, and some scientists, especially here also from Germany, have suggested, Alfred Wegener Institute and so on, that it might actually be decreasing low clouds during those years and those low cloud decks that led to this basically gap in warming in recent years. And the open question then is this just internal variability, maybe linked to some sort of unusual surface temperature state of the oceans, or is it a climate change signal? And we are tackling this from a very simplistic point of view in the first place. So I think this is very easy to understand if you are doing machine learning already, because machine learning in many cases is a regression, right? And already years ago, so this is a review paper I linked to here, and this is also why this plot is weirdly coarse. This was not me, this is actually how I took it from this review in 2017. There was something called a cloud controlling factor analysis, which, for example, looked at how do climate models and observations behave if you just look at these low cloud decks and regress their radiative effects, so cloud, for example, reflectivity, how much sunlight is being reflected as a function of underlying changes or variations in sea surface temperature, in relative humidity in the atmosphere, in vertical velocity, which is also important because sort of turbulence and atmospheric stability can influence cloud formation. And yeah, this has been done for quite a few years, and what people have shown is that you can apply this to historical observations and compare climate models then in terms of their sensitivities to these factors, environmental factors, to observations, and find maybe which models are more realistic in capturing these large-scale controlling factors, relationships to cloud variability. And clearly this is just a linear regression, so you were typically limited to maybe 5, 6, 7 different variables in those particular regions. But what I found particularly interesting is that these relationships, also in climate models, seem to hold under strong climate forcing scenarios. So this is almost like a climate invariant constant, okay? So if you know your sensitivity of clouds to underlying surface temperature changes in the past, then you find a very similar relationship in the future for the same climate model. Just this relationship would be different for different climate models, right? So the question then is, okay, if you could replace those sensitivities by the observed ones, what would be potentially the cloud changes that you see given different surface temperature, humidity, and vertical velocity changes in the future? And now you basically have got the regression there, but it's linear, right? So the extension of this was to build similar controlling factor frameworks, where we basically use a machine learning function to predict any target variable of interest. So in this case, this would be clouds as a function of the controlling factors. And this would also allow you to capture in this X a much more complex physical state of the atmosphere, not just 5 or 6 different variables averaged over a large domain, but you could really look at underlying patterns of surface temperature variation and so on. And then the key challenge is here, and you can imagine this, I will also show you later on, that you still want to keep a climate invariance property. Because potentially if you apply a machine learning function to do this mapping, so potentially nonlinear, then it could be that you have high predictive skill on historical observations for this relationship, but that if you applied the same relationships to future climate change scenarios and trends, for example, in variables, that this would fail. I will give you an illustration of this for exactly the same plot later on. But if it works and you have this climate invariance, then for each climate model, you should be able to learn a function that has both historical skill on observations and on climate models, and skill also in an extrapolation case under future climate change. And if you do this for, let's say, 40 different climate models or so from the archive, you could then sort of derive what your method uncertainty is in the prediction for the climate change state. But the key property here is climate invariance. And we've done this for clouds, just as an example, where the predictant then is cloud radiative effects, so both sunlight reflected coming in and also their greenhouse effect. And then you regress this against patterns of underlying environmental factors. And we usually do this here still in a linear framework if you want to go through the extrapolation, so something like ridge regression, for example. And we showed that including these patterns and looking at smaller regions of cloud variability here, we were able to much better predict not just historical variability, but also the future response for each climate model. We were able to capture much more realistically the variability. And whereas previously people only showed this for short wave to hold, we could now also predict the long wave greenhouse effect suddenly by taking these larger patterns. So that really just by moving very simply from a multiple linear regression to a higher dimensional framework, still linear, it outperformed everything we had for 10 years in the same approach, right? So very simple ideas can really make a big change here. And just to highlight why we use sometimes linear frameworks in this context, I did this once with the target variable as this target variable surface temperature. And what you can see is that if you just fit a simple random forest model, which as many of you will know is clearly the worst case in terms of extrapolation because it will not predict anything that it hasn't seen, then if you had your future response within a climate model and a future scenario in black, and in red would be your climate invariant function that basically learns linear relationships and maybe doesn't capture some of the extremes so well in the future, but it does capture the overall trend, and the random forest would just level off, right? So it would drift away from this curve, so you'd not be able to use this more complex function. You would see similar stuff for neural networks, and this is mostly, so if you look at the actual monthly or even daily predictions of this, you in the year 2080, which is under a much warmer scenario, you would see that the random forest would basically predict the summer can't get hotter, right? Because it hasn't seen this data before. So you have to be very careful about your choice of method, and sometimes a simpler method can outperform in this extrapolated response the more complex method. So this is always the challenge. Maximilian highlighted this too, if we model a non-stationary system. Okay, I definitely don't have time for this, so I will just jump through this. So unfortunately, I can't talk about the stratosphere here, but there are other factors of uncertainty, right? So stratospheric water vapor models differ between basically 0% response under something as abrupt as 4 times CO2 increase and a 250% increase in water vapor. So that's a huge gap that we could constrain using this method, and that's very important as well for global radiative forcing. And yeah, so using this approach, we were able to write, I would say, 2 arguably high impact publications leading this in PNAS and Nature Geoscience. So simple ideas can sometimes go very far away where you derive these sorts of observational constraints on climate model uncertainties. We've also done this directly on surface temperature as a target, on daily fluctuations. So this now allows us to constrain individual heat extremes, like the 2003 heat wave, for example, in Europe. So this seems to work extremely well. And we've also done similar ideas, but more from a causality point of view for precipitation constraints. So again, this was published already a few years ago now, but we have recently updated this with Kevin De Beer from DLR to learn high-dimensional relationships to basically constrain how well climate models capture dynamical relationships, and from this, how we model precipitation responses. So we were able to derive some observational constraints on this as well. So these are just some of the ideas how we by taking advantage of machine learning, being able to learn both from observations and from climate models to then be able to compare relationships and constrain the future response without having to improve every single climate model individually, which takes a lot of development effort. Okay, and on this I will end, and I think there's also a big role to play for weather forecasting models and foundation models and so on that Maximilian touched on in this context, but maybe we can discuss this over coffee. Okay, thank you.